All right, I think we'll get started. I hope everyone can hear me. Um, so I'd like to welcome you all to the first RISC-CAN webinar on compound extremes. And we have two very nice speakers coming up this morning, or afternoon, actually for many of you. Here it's 7 a.m. in California. The RISC-CAN, many of you are probably rather familiar, but in case you're not so much, I'll describe the overall RISC-CAN a little more in a couple of slides. Essentially, it's just a framework for bringing people together around extreme events and their impacts kind of broadly within the climate system. So because it's just a framework, it's really given life by active participation. So we're hoping to have a lot of kind of engagement. In a webinar format, it's a little less engaging, than some of our other events, but we're still hoping to have active question asking, for instance, after each of the talks. It's also a relatively informal thing, and it's still evolving. I'd like to acknowledge, of course, at the bottom, the funding for the RISC-CAN comes from the three organizations listed there. And the Compound Events Group is just one little arm of the overall RISC-CAN. So this is a slide that Marcus Reichstein, who's one of the lead actors of the RISC-CAN, has often showed in his presentations. And I thought it was probably worth revisiting here just for a second. So this is the results of a survey of experts at the World Economic Forum a couple years ago, looking at the expert judgment of the impact on the y-axis and likelihood on the x-axis of different types of global threats to stability and prosperity. And you can see in the green diamonds, primarily environmental disasters, extreme weather events, climate change, mitigation and adaptation issues, biodiversity loss. And then I've additionally circled in green other types of disasters that were categorized under other categories for the purposes of the survey, but which are quite relevant to compound extremes, from water and food crises to infrastructure, urban planning, migration, and disease. So a lot of different types of things that we're interested in, and many of them with a high impact and likelihood in the next decade to few decades. So the RISC-CAN, this is also just from the website, kind of a thing that they often show as a one-page overview. It's a framework for bringing people together kind of around risks, extreme events, and sort of how to improve our treatment of them as a global scientific community. So it's not exclusive to physical science by any means. In fact, we're trying specifically to reach out to non-physical science people, but clearly the basis is in physical science, especially for compound events. And then this is the kind of more details about it, and you can see the compound events group at the top. Kai and I are now the main people, and then there's other groups as well who we're going to be working with more as the RISC-CAN further develops. And then the main contacts for the RISC-CAN are done at the bottom there. And so to give a little more about the compound events group now, and this is Kai and I's initiative. Essentially, our goal is to bring people together and kind of share research based on one, organizing activities like this, and then two, just serving as an information repository for people to kind of look at. So events calendar, membership directory, the mailing list maybe should go more under repository, but we'll be kind of compiling it based on your inputs. So, research highlights, and then of course the webinars we're planning on doing every 4 to 6 weeks or so. And then when conferences are again possible, we would like to have some social networking types of events in association with those. And then my last slide here is just from the compound events group spreadsheet, which many of you have probably already seen. We have a timeline of upcoming events, and this is crowdsourced, so please add things to it. I'll put the webinars here as well in the future, and there's a little tiny URL for it down there, and then our addresses are already on there, but just copied them here as well. So with that, I will hand it over to Kai, who will talk just for a couple minutes about the webinar series more specifically, and then we'll jump into the two talks.
Thanks a lot, Colin. Yeah, this webinar series was initiated as a way to bring this community together a bit as part of the RISC-CAN framework, and ideally serves as an inclusive way to share information within this field of research that touches so many other aspects within climate science, but also within fields of engineering, statistics, mathematics, and so on. So our idea with this was to really bring all of these fields together and enable a way of knowledge sharing without having to meet all the time. So our plan is to host people that have recently published within this field or have been publishing for a while, and their research would be of great interest for this community. So in general, we're interested in science based on the physical drivers, mechanisms, but also the future changes of compound extremes, new conceptual approaches, statistical methods, but also more applied aspects such as disaster risk management, societal aspects such as economic or health effects. For today's webinar, which is the first of this format, we have two talks, which both are planned to last 20 minutes, followed by a 10-minute discussion. To make this a nice experience for everybody, we would ask you to mute your microphone and deactivate your camera during the presentations. And then during the discussion round, use the raise hand function to signal that you have a question or to post a question in the chat. Colin and I will then try to come up with a list of speakers and then call those people up one after the other. I'm really pleased to see that we are 116 people now, if I can see that correctly. So we are gaining experience with how we can enable a discussion with so many people in a room. It's going to be very interesting, but I think it will work best if we stick to these rules and let us kind of pick those people. So let's dive into the talks of today. Our first speaker is Dan Cooley, who is a professor and associate chair of the Department of Statistics at the Colorado State University. Dan works on extreme value analysis related and motivated by problems involving risks from extreme weather events. His recent research has focused on theoretical, statistical, and applied studies of multivariate and multi-cause extremes, including fields of air pollution, heat waves, and hydrometeorology. His talk is titled Compound Events from a Statistics Perspective, Multivariate Extremes. And with that, I would hand over to Dan.
Perfect, thanks, Kai.
Okay, hopefully you can hear me, and okay, first of all, can everyone hear me?
Yeah.
Yeah.
Okay,
Everybody's muted, so.
Hopefully you're also seeing my screen. Let me begin with a quick apology. I teach in less than an hour, and so I'm not going to be able to sit through the entire second talk. And if there are things that we're not able to cover during my talk and question and answer session, please feel free to reach out to me via email or any other method. So my talk is titled Compound Events from a Statistics Perspective, Multivariate Extremes. And my idea was to give some background on multivariate extremes. And so I sent my abstract to Colin, and Colin very tactfully and politely replied, "Sounds great, but I think the audience is a little bit more sophisticated than you're giving credit to." And so the talk has changed a little bit. What I'm going to try to do is give a very brief background in the first, say, 10 minutes, and then talk a little bit about some current work that shows maybe some of the potential of these methods. So the first slide I pretty much want to skip, but I think most people are familiar with univariate extreme value theory, which hopefully you're also able to see my cursor here. You may be familiar with distributions like the generalized extreme value distribution or the generalized Pareto distribution, and kind of the philosophy of extremes is to let the tail speak for itself. And so we do something that seems strange at first by throwing away most of the data and only retaining the extreme events. But this allows us to do things like extrapolate into the tail. And perhaps to illustrate this, I could, if given more time, I could do an analysis where we use extreme value theory to characterize the tail of this Fort Collins precipitation time series, we estimate the probability of exceeding an event greater than this largest event. And if you use extreme value theory and a pretty straightforward application, you get a return period of 146 years. If you use a naive approach where you try to fit a distribution to the entire data set, and it's an inappropriate distribution, it's a gamma distribution, which fits the bulk of the data quite well. But lots of tests you look at and say, this distribution fits very well, but it fits the tail very poorly, and you can get a ridiculous estimate of a return period of 35 million years. So there's reason to use extreme value theory, and perhaps the takeaway message from univariate extremes is using a non-extreme model to estimate tail quantities can give you really bad results. So the idea of multivariate extremes is the same. We want to restrict attention to the tail and let the tail tell us what's going on there. And so what I have here is some data where on the x-axis is wind speed and on the y-axis is dryness. Just think negated humidity. So up in this right-hand corner are windy, dry days. And this is a station in Southern California. Fire risk is something that we'd like to be able to quantify. And so the days up here in this upper right corner are days which are at increased fire risk. And so what we often do in extremes is try to give probabilistic assessments of rare events. And so we might want to assess the probability of landing in this larger red box. I'm going to call that R1. What is the probability that a given day in this fire season falls in this red box? And so we need to find a parametric model for this data. It needs to be parametric because non-parametric methods kind of fall apart in areas where you don't have a bunch of data. And we don't have a nice parametric model for data that looks like this. If you looked in a catalog of multivariate distributions, that first of all, the first half of that catalog would be about the multivariate normal, because that's the multivariate distribution that we know the most about. And then there are a long list of other distributions that people have come up with, but none of them were designed to fit this particular data set. You might consider transformation, and we are going to consider transformation for this data. But very importantly, we need to capture the dependence between these variables way out here in the tail. And so the first thing to notice is that our usual measure of dependence, correlation or covariance, is not going to be very useful, because correlation or covariance talks about spread from center, and the center of this data is nowhere near the tail, and the dependence at the center probably doesn't tell us how wind and dryness can occur together. And they can occur together due to a phenomenon known as the Santa Ana winds, or the Santa Ana conditions, which cause dry, windy conditions to occur together. Another thing that is important is that direction matters. We are very interested in the upper right tail. We are not at all interested in the lower left tail, because those would be calm, moist conditions which have no influence on fire at all. And again, so correlation, which looks in both directions from the center, isn't paying attention to direction. And then a final idea that arises is the notion of asymptotic dependence. And I'm going to talk about that in the next slide, but I'm going to try and convince you that this data appears to be asymptotically dependent. So the notion of asymptotic dependence, the definition is given by this equation on the slide, which says essentially what it says is the probability that X gets big, given that Y is big, goes to 0 as our definition of big gets bigger and bigger and bigger. Now, we have the X being the CDF of X and the CDF of Y being applied to those random variables to normalize them, to put them on common scales. But essentially, like the slide says here in the middle, asymptotic independence implies both variates cannot be at their most extreme levels simultaneously. And that's not true for the data that we were just looking at, where we saw days that were both at their windiest and at their driest at the same time. And this plot here is an empirical estimate of this conditional probability. And we see that we see that it appears to be leveling off here at about somewhere between 0.2 and 0.3. It gets at the very top, it gets very hard to estimate because we don't have enough points up there. But most extreme value people would look at this and say this exhibits asymptotic dependence. About 30% of the time, when conditions are at their most windy, their conditions are also at their most dry. Okay? So asymptotic dependence, if data exhibits asymptotic dependence, this model, this parametric model that we need to use, also has to have asymptotic dependence, or we're going to misestimate the probabilities of landing in a box like this. And that's a real problem, because most bivariate models exhibit asymptotic independence. If you look at a catalog of multivariate distributions, for instance, the multivariate normal exhibits asymptotic independence. And so using those to extrapolate or to quantify probabilities in the upper tail for data that are asymptotically dependent is problematic. And so I mean, the framework that I use to describe multivariate extremes is called multivariate regular variation. And it has a fairly complicated, seemingly complicated mathematical formulation, but in a nutshell, what a multivariate regularly varying random variable is a multivariate heavy-tailed distribution. And the definition says this. It says that the distribution of large points, so points way out here, far away from the origin, can be described in terms of their radial and angular components. The radial component is just the magnitude of the vector. The angular component is just the direction that it is that is associated with the vector. And these radial and angular components, importantly, become independent as the magnitude increases. So we can separately model those, and that's critical for statistical modeling. The radial component decays like a power function, so that gives us our heavy-tailed behavior. And the angular components are described by a measure. We can think of it as a probability measure that lives down here on the unit ball. And so this measure H tells us what angles are likely and what angles are not likely. And if that distribution has most of its mass in the center, then what we will have is most of our large points will occur here in the middle, meaning that we have strong dependence. Large values of X correspond with large values of Y. And if that distribution H has mass at the corners here near the axes, then what that says is we're likely to have large points in that direction, which would mean a large value for X and a non-large value for Y, a relatively small value for Y, or vice versa. And this framework is, you could argue that it's right because there is theoretical justification for this framework. It's very closely tied to the multivariate extreme value distribution. So the probability theory that gives us the GEV distribution, when expanded to multivariate cases, is very closely tied with this formulation. But as a statistical model, it's also useful because it is a model that achieves asymptotic dependence, and there aren't many models out there that do that. It's a model that only describes the large points. The definition says nothing about the small points, and so we're not characterizing the entire distribution. We're only characterizing the distribution of the large points. And so the modeling is only going to use the large points. And one thing that I like about regular variation in the positive orthant, the way I've described it here, is that it only looks in one direction. We're only going to look in that upper right corner, and we're not going to try to describe things in other directions. So getting back to our data, the way that this works is we would start with our data on its natural scale, and we do have to perform a transformation. And so I would transform this data so that it fits in our regularly varying framework. And so this center plot is the same plot of data after marginal transformation to something heavy-tailed. And it looks like most of the points have disappeared, but what's actually happened is most of the points are gathering down here near the origin, and we're not going to try to describe those. We're only going to try to describe kind of the large points that we see. And what we're going to do is we're going to essentially fit a model to that angular measure. We're going to try to describe the distribution of directions of the large points. And then what we can do is we can assess the probability of landing in this red box. This large red box corresponds to this larger red box here in the original picture after transformation. And so we can estimate that probability. And with my model, I estimate that a randomly chosen point in this season has a probability of 6.8 times 10 to the negative third probability of landing in that box. What that translates to is about 6 days per 10 seasons would land in this larger red box. Now, because we didn't choose anything that's too extreme, we can actually just count the number of points that land in that red box, and the empirical probability is 4.9 times 10 to the negative third. So we perhaps are overestimating it a bit with this model. Hopefully not terribly. I would argue that if you did something similar, there's a lot of talk about copulas, and kind of everybody's favorite copula, or at least the easiest copula, is the Gaussian copula, because it translates to our most familiar multivariate distribution. If you were to transform the marginals to be normal rather than heavy-tailed like I did, this is the plot you would get. You could try to use your Gaussian model to assess the probability of landing in this upper right corner, and I would argue you get an underestimate of that probability. So these bullets down here just let you know that we can, not only can we come up with point estimates, but we can get return levels, or I'm sorry, we can get confidence intervals. And we can do things like we can estimate the probability of an even more extreme box. This box here would have an empirical probability of 0 because there are no points that land in that box. But we can still use our framework to perform that extrapolation and estimate probabilities. So that's that's the half of the talk about the background of a way of thinking about multivariate extremes. And there are other ways that multivariate extremes get described, and they are typically, most of the methods are very close to this method of regular variation. They have very strong connections. And so if you hear about the multivariate extreme value distributions or the multivariate Pareto distribution, those can be linked to this framework that I used here. So I'm going to very briefly talk about some work that we've been doing recently. This framework is fine in 2 dimensions. You can imagine modeling it, but when you have a whole bunch of dimensions, things get much more difficult. And so what we tried to use was this framework to describe patterns in extreme precipitation across the US. And so we've got 1,100 stations. And so we have this essentially 1,100 dimensional random variable that I need to describe the extremes. So we can't completely model this angular measure, which talks about the directions that are common. And importantly, I want to point out that our aim here is quite different than what's typical in extremes. Typically, what we try to do is what I just showed, where we try to give a probabilistic estimate of an extreme event. Here, the question is kind of more vague. Imagine an atmospheric scientist comes to me and says, hey, I've got this data from 1,100 stations. I want to understand patterns in extreme precipitation. Now, with that question, if that scientist had not said extreme precipitation, if they just said patterns in precipitation, a lot of people would say, hey, one way to attack that would be to perform a principal component analysis or an empirical orthogonal function analysis of the data. Essentially, take the data, estimate its covariance matrix, obtain the eigenbasis of that given by that covariance matrix, and try to understand patterns through the patterns occurring through those eigenvalues. So you could look at the eigenvector, you could look at the time series of its eigenvalues, and you could try to say, okay, what does this time series say about the signal given by this eigenvector, which seems to be an East Coast signal. So our aim was to do something similar for extremes, but it's different because we can't use the covariance matrix. We need this idea of basis and vector space, and we want to work in just the positive orthant, and so we have to define a vector space for the positive orthant. And so we need to do something different for extremes. And so I'm going to skip over the method mostly, but essentially we do have to pre-process the data like we did in the previous example. We have to do some marginal transformation to make it fit into our regularly varying framework. But then what we can do is we can summarize the tail dependence in a matrix. It's not a covariance matrix. It's a matrix which captures the extreme dependence in this one direction. We call that the tail pairwise dependence matrix, but importantly, this matrix is positive definite. So we can do an eigen decomposition. This eigen basis is most efficient in a certain sense, and so it makes sense to look at the first eigenvector, then the second eigenvector, and the third eigenvector sequentially. And because it's a basis, we can represent any event. So here are our eigenvectors that we obtained. The first one is kind of a continental signal. The second one is an East Coast signal, I would argue. The third one is a West Coast signal. The fourth is again an East Coast. It kind of partitions that earlier East Coast signal to be very coastal. The fourth contrasts the South Central versus the Midwest, and the fifth does that, and the sixth contrasts Northeast versus Southeast. We looked at hurricane season, so we were interested in East Coast signals. So essentially, we are going to look at the behavior of E1, E2, and E6. And so I'm running out of time, so I'm going to skip over this a little bit. But if we look at the time series for the coefficients applied to that continental signal, here is that time series, and we asked ourselves, is there something going on with this time series? And one of the things we thought is maybe there was a little bit of an upward trend in the extremes. So we did a quantile regression test. The slope turned out to be estimated at 0.002 units per year, but importantly, the p-value for whether that slope was equal to 0, the test of the hypothesis test turned out to be 0. And so what we were able to do is we can conclude that there is a significant positive trend in the, well, in the 0.95 quantile of the continental signal for extreme precipitation. What we were also able to do was we looked at the second eigenvector, which corresponded to an East Coast signal, and this is the coefficient this is the time series of coefficients for that. We looked at that and we see that the negative spikes, which turn out to be the direction of interest because our East Coast signal, these blue values essentially say that this is in the negative direction. So a negative direction paired with a negative coefficient would give us a positive value on the East Coast. We looked at this time series and we paired it with the El Nino signal. So gray is neutral, red is El Nino, blue is La Nina. And it sure looked like a lot of the negative spikes were paired with La Nina events or conditions. And we performed some hypothesis tests to see if there was a connection between the La Nina signal and these events. And again, we're seeing something significant. Now, this is not earth-shattering because there's been previous data that says that there's a connection between La Nina and hurricane events. But this is a different way of looking at it. I think I'm out of time, so I'm going to skip this slide, but we also found some interesting behavior which said that perhaps La Nina puts the Northeast United States at increased risk as opposed to the Southeast. And so this is something that is new and I don't think has been explored. And this is certainly not confirmatory, but I think that what this method does is it allows us to explore extreme events in a new way. And so this finding here that I'm showing on this slide would be something perhaps for further investigation by people through other methods, either using climate models or just looking at the data differently. So I definitely want to keep to our time frame, and I think I've about spent my 20 minutes here. So let me just open it up to questions. Colin, do you want to run things from here?
Yeah, maybe Kai can help me for a second.
Sure, what's up?
Well, I'm not sure if I missed people raising their hands. I saw Pascal and Mojtaba's questions in the chat. Well, Mojtaba isn't really a question about the talk. I'm afraid some people raised their hands and I didn't see it.
No, I don't think anybody.
Okay, maybe not.
So far, just again for all the people participating, if you go to the participants menu, there's a raise your hand. You can click on when you have a question, and we will call you up to ask. Alternatively, you can also write your question in the group chat.
Okay, so in the meantime, I'll read Pascal Yu's question here. His question is, how would you account for the density or lack of points? I guess, sorry, Pascal, I'll unmute. Oh wait, Pascal, you're unmuted, so please clarify. You can ask a question yourself.
Okay, can you hear me?
Yes.
Okay, sorry, I didn't see the raise hand. I don't have a raise hand button. So my question is on when you compute the EOFs, so the number of points is not, okay, you look at the map, there are more points on the East Coast than on the West Coast. So would this affect the results on the EOF or the extreme EOF you compute?
I don't think so. What the extreme EOFs are trying to do is trying to efficiently break down the signal, and so one could argue that perhaps that there's redundant information on the East Coast, that we probably wouldn't need all of the points that we have here on the East Coast to get to see that signal. Now there's no problem in including them either. if you wanted to say something meaningful about extreme precipitation in Wyoming, which is this state, which I don't know if you're able to see my cursor or not, but it's a state that's mostly black. We have very few stations in Wyoming. It'd be very difficult to use this kind of analysis to talk about extreme behavior in the state of Wyoming because there's just not enough stations here. And that's really not the purpose. What we're trying to do is trying to look at extreme precipitation on kind of the macro scale, on the large scale, and say, are there trends that we can find by pooling all this data together in a way that hasn't been done yet, extracting a signal from the EOF analysis, and then by analyzing those signals rather than the individual stations or themselves, can we see trends on the macro scale? And one of the things I think we clearly see is that there's an overall upward trend in this continental signal. And so I think that's interesting because what that's saying is, to me, is that extremes are getting more extreme in this season across the continent.
Okay, thank you.
All right, we have another question here. Alaba, sorry if I mispronounced your name. Please go ahead and ask your question. All right, there we go. So you should be unmuted.
Hello, can you hear me? Yeah.
Yeah.
Yes.
Yeah, my question was about because you discussed about asymptotic dependence, but in some cases data is asymptotically independent, but still more dependent than Gaussian bivariate distribution. So, how did you have this situation before, or did you?
So asymptotic independence is in fact even more challenging to model well than asymptotic dependence, kind of for the reason that you described. You don't want to fit a Gaussian model to it just because it's asymptotically independent, because the tail dependence could be stronger than what's captured by your Gaussian model. And so modeling asymptotic independence, and getting it right is even more challenging. And there are some models that are out there that can do that. And there are more parameters that describe kind of that level of dependence in that case. I didn't get into that here, obviously. I would say, I guess a defense for asymptotic dependence would be that it's overly conservative. If anything, you're going to overestimate the probability of this risky event happening. Now, there are consequences to that. You could spend way too much money building your dam or building your infrastructure to protect yourself against an event that is less likely than you estimated. But I guess that's a partial answer. The first answer is yes, there are methods out there that handle asymptotic independence. They are even trickier than this case. And this case is conservative. You could use it as a first step and then see if it needs further refinement with the extra effort that an analysis where you account for asymptotic independence would allow you to have.
Thank you.
All right, I think we'll do one more question since we're just a couple minutes behind. Joel, I'll unmute you here.
Yes, thanks for the great talk. It was very interesting. I was just wondering concerning your multivariate angular variation method you've introduced in the beginning. What would you say are the main advantages relative to using multivariate extreme value theory or copulus?
Good point. So I would say this fits under the umbrella of multivariate extreme value theory, but you could use a multivariate extreme value distribution, which at its core is a multivariate regularly varying distribution. One difference here is that essentially I'm doing a framework that allows me to do threshold exceedances. When I do my analysis, I'm using all of the daily data that exceeds a threshold. Multivariate extreme value distributions are more, or or another way of saying that is multivariate max stable distributions are really used for block maxima type data. And you could argue that you lose some information by using just the block maxima. There are some advantages too. It makes dealing with the data perhaps a little bit cleaner, because you don't have this messy business of choosing a threshold. But that's one difference. Copula methods are the downfall. The potential downfall of copula methods is you could choose a copula that you think fits the data well, and be fooled by the bulk of the data and miss and pick a copula that has asymptotic independence when your data is asymptotically dependent. So there are risks with general copulas analogous to what I showed here with the Gaussian copula.
Okay, great, fantastic.
All right, thank you very much, Dan. Now we'll switch over to our second talk by Marleen. Marleen de Ruiter is a PhD student at the Free University of Amsterdam in the Water and Climate Risk Group. Her background is in resource management and disaster vulnerability and recovery. Her current projects include improving the modeling of consecutive climate-related disasters at global and local scales, and developing ways to better understand how adaptation measures affect disaster risk in complex, or you might say realistic, contexts. So with that, I'll turn it over to Marleen to start her presentation.
Let me share my screen. Let's see if that works. Does that work?
Yeah, that looks good.
Cool. Well, thanks, Kai and Colin, for inviting me. I just want to apologize to those of you who have seen me present on consecutive disasters before. I think the first 6 to 8 minutes will be explaining the concept of consecutive disasters, and some of you may have seen that, but I promise after that there will be more new things. So does anyone recognize this picture here? I see there's a chat thing. Oh, sorry. Go back. So this is a picture of the 2011 Tohoku earthquake in Japan. And that earthquake then set off a chain of events, including a tsunami, which caused a flood, and it set off fires. And so one event was responsible for a chain of following events. In another example, in the case of Nepal, the country was hit in 2015 by an earthquake, and only 1.5 years later, when recovery was still underway, the country was hit by flooding. And so this caused a major setback in terms of the recovery efforts that were happening locally. The Philippines are hit annually by approximately 20 tropical storms or tropical cyclones. And in an attempt to mitigate the impacts of those tropical cyclones, people have started to use concrete and stone to mitigate the damages to their houses. But last summer during an earthquake, it turned out that especially those buildings that were made out of concrete and stone were actually much more vulnerable to the impacts of earthquakes. You probably all also remember the events that happened about a year ago, around this time of the year, when 2 cyclones hit the African East Coast only 6 weeks apart from each other. And one of the many challenges that occurred here was that after Cyclone Idai hit the East Coast of Africa, many governments spent all their financial and other aid resources to help people recover, not realizing that 6 weeks later, another event was about to happen, which meant that by the time that Kenneth hit the coast, many of those resources were either limited or completely depleted, which then really impacted the post-disaster recovery efforts. And finally, maybe you noticed last week, Tropical Cyclone Harold hit the Solomon Islands while they're obviously also still dealing with the corona crisis, and this really compromised the local aid efforts. So these are all examples of what we call consecutive disasters. And we define those consecutive disasters as 2 or more events whose impacts overlap both spatially and temporally, while recovery from an earlier event is still underway. And so this is irrespective of whether there's a dependency between the hazards or whether they're monohazards, etc. And the international community has called upon scientists to move away from this hazard silo thinking and gain a more comprehensive understanding of disaster risk. It's important to note that this is not just an issue in terms of our scientific capabilities in modeling risk, but it's also an issue of risk management. For example, in most cities, the earthquake engineers are in a completely different department than the flood protection engineers. And so even if we were to have perfect consecutive risk modeling capabilities, due to these institutional fragmentations, we would still not be able to properly plan for and address consecutive risk. So there's different challenges at play when we try to assess or deal with consecutive disasters. And we kind of group them into three categories: the spatial dynamics, the temporal dynamics, and the fact that you need to account for multiple different types of hazards. And over the course of this presentation, I'll try to touch on all of them, probably not in this particular sequence. So the main differences between the common single hazard approach, which is depicted in the top panel, and the consecutive hazard approach, which is depicted in the bottom panel, is, I think, a couple of things. So first of all, commonly single hazard approaches tend to assume that a next event happens when recovery from an earlier event has been completed. So as you can see, like after each event, we first reach a new stable level before our next event happens. There also seems to be the assumption that despite the fact that an earlier disaster has happened, that the rate at which recovery occurs does not change. So let's take a closer look at what we think happens in the consecutive event and the different dynamics that we need to take into account. So at the x-axis, you see time, and at the y-axis, we put an indicator of impact. So in this case, we use the quality of the built environment, but obviously you could use any indicator of impact. And so for simplicity, we assume what we call static exposure, meaning this community doesn't build new houses. We don't assume that there's like a change in the number or type of buildings. So let's walk through it. So first at T1, an earthquake hits this village. And obviously after that disaster, they start to try to recover from this event. And so normally in this like single hazard paradigm, we would assume that it just goes up to like that stable level. But actually, as we've seen in the examples that I discussed earlier, it can happen that another event occurs while recovery is still underway, which can actually cause, as it shows here, a major setback in the recovery process. But it can also cause the rate of recovery, delta R, to be actually slower than it was after that first event. So this is a really unfortunate community, and so they're also hit by a flood. But this is just to show you that not every sequence of events needs to be a consecutive event. Like in this case, they recovered from the flood, and so it's not a consecutive disaster. And then there are two different types of consecutive events, and I show these because there's two different effects, I think, at play. So first of all, a sequence of consecutive events doesn't necessarily need to be worse. So here, in case of the tropical cyclone, obviously the buildings are already more vulnerable due to the wind damage. And so when a landslide occurs, you see that there's like even more damage than they had before. But conversely, here in case of the earthquake, if the earthquake is so devastating and almost none of the buildings are still standing up, then the fact that there's fires breaking out after that earthquake doesn't do that much more damage to the city. It's also important to note that this concept changes with what you put or what you use as an indicator of the impact. If instead of the quality of the built environment, I had used the well-being of people, after this earthquake, all the people would have been forced to be out on the streets. And so obviously they're more exposed and they're more vulnerable to a next event. And so you get a completely different dynamic. So that's all theoretical. Let's move on to more like what we've done to calculate this. So first we calculated the absolute number of consecutive disasters, looking only at two hazard types, earthquakes and tropical cyclones. For earthquakes, we use the USGS ShakeMed data that's available from 1960 until 2016. And for the tropical cyclones, we use the IB tracks for that same time frame. And then for each administrative level 2 area, so that's similar to like states and provinces, we calculated the absolute number of consecutive disasters accounting for 2 different time windows, so 3 days and 30 days, by which we mean that we look at any type of interaction, either type of sequence of either earthquake following an earthquake or earthquake following a tropical cyclone, etc. And after that, we also looked at the relative frequency with which consecutive disasters occur. And we used the same 2 empirical databases for tropical cyclones and earthquakes. And what we found there is that almost 10% of the global population actually faces a relative frequency of 20% or more of experiencing a consecutive disaster within a time window of only 30 days. And that's when we only account for 2 hazard types, so let alone if you were to include other hazards. So seeing that there's such a high frequency of experiencing consecutive disasters, it's also important, I think, to look at adaptation measures. So earlier I talked about that case of the Philippines where to mitigate the impacts from tropical cyclones, people started to use concrete and stone to prepare their houses. But at the same time, that made their houses actually more vulnerable to earthquakes. And so this concept, these like potential adverse effects of a disaster risk reduction measure, we refer to as an asynergy of a DRR measure. Another example would be that in California along the coast, houses are often built on stilts to prevent them from like flooding, but it actually makes them more vulnerable to earthquakes. And so I just want to show that using these schematic frameworks. So generally after an event happens, we realize that we need to do something. And so here, after a flood event, this village implements a flood disaster risk reduction measure. In this case, they start using masonry for their buildings. So like flood waters can less easily infiltrate the buildings. And so there's a decrease in the flood risk levels. But at the same time as they implement those flood DRR measures, there's an increase in the earthquake risk. Because using masonry makes the houses more stiff, and so they are more likely to break during an earthquake. The reverse happens here for an earthquake DRR measure. But what's interesting is that the total risk can also change. So here, despite the fact, as in the flood DRR measure case, so despite the fact that the earthquake risk actually increases, the total risk still decreases. Whereas here in the earthquake DRR measure case, the opposite happens. And so we thought this was very interesting to look at in a case study. So we assessed this using floods and earthquakes for their measures in Afghanistan, and we used World Bank data. They have collected a whole bunch of data on all the residential buildings and their types in Afghanistan. And so this image just shows a selection of these types. So here on the left, you have adobe buildings, masonry buildings, reinforced concrete, and steel frame. And so what we did is calculate the average annual losses for each of the hazards in the current situation and into DRR scenarios. So the flood DRR scenario is similar to what I just discussed. We upgraded all the adobe buildings in Afghanistan to masonry, so making them more flood resilient but more earthquake prone. And at the same time, in the earthquake DRR scenario, we upgraded all the adobe buildings to wood buildings. Wood buildings have a higher chance of buoyancy, and water can more easily infiltrate. But at the same time, wood buildings allow for a sort of sway, and so they're less likely to get damaged by earthquakes. But with that change, with a change in your exposure that large, as you can imagine, upgrading an entire adobe building stock of a country from adobe to, for example, masonry also means that the value of your exposure increases, which would inherently mean an increase in your average annual losses. If you still want to be able to compare the DRR scenarios with your current scenario, what we did is calculate the relative AAL. So we calculated what we call the risk ratio. So we divided the absolute AAL by the value of the exposure in each of these circumstances, into these cases. So these are the 2 risk maps. So this is for flood on the left and for earthquakes on the right in the current situation. As you can see, it really follows the hazard map. And then what we did is we calculated the risk of each of these 2 hazards in each of these 2 DRR scenarios. And so we got 4 more maps. So this is the flood risk within the flood DRR scenario. Then we get the earthquake risk in the flood DRR scenario. We get the flood risk in the earthquake DRR scenario, and we get the earthquake risk in the earthquake DRR scenario. And I'm not sure if it's like showing on your screen. You have to take my word for this. So for example, if we compare B and D, so the earthquake risk in the flood DRR scenario and earthquake risk in the earthquake DRR scenario, in the flood DRR scenario, the earthquake risk actually is much larger than it is in the flood, in the earthquake DRR scenario, and the opposite happens for for floods. And so that also allows us to assess what would be an optimal situation in terms of flood and earthquake DRR measures. And so we calculated per district this percentage reduction in risk ratio using either the flood DRR scenario or the earthquake DRR scenario. And in blue, you see everywhere where the flood DRR scenario is more beneficial in reducing the risk ratio. And in red, you see that for earthquakes. And so what we found is that, well, about 2/3 of the country would actually benefit from flood DRR measures. The benefits are not that high. For example, here, this is Iran, so here, this is the west of Afghanistan. In Shibko, this is the highest reduction. This is a 16% reduction in terms of risk. Whereas for these red districts, where earthquake measures are more beneficial, we found much higher impact in terms of reduction. We found like over 30, over 40%, for example, here in Khoshtra, Feeding, or in Bak. So we started off globally, then we went nationally, and I want to touch on some local aspects. So one way of thinking about adaptation is migration, which obviously includes forced migration, displacement, or migration because people realize that they need to move away out of harm's way. And this is a study we're still working on. We're working on this case study for the Philippines. And what we've done here is we just mapped these three hazards that occurred between 1980 and 2015. So note that we only included very damaging earthquakes. And so what we're doing is comparing that to where the local population is and also how they move throughout time. We obviously have to correct for other reasons that people migrate. And there's just one final thing I would like to point out here. We just kind of randomly selected this admin 2 area called Zambales. And what we did is create a sort of a barcode of all the disasters that have happened over that time period of 1980 to 2015, also including floods from the Darfur Flood Observatory. And so earlier when I discussed that schematic graph of consecutive disasters to explain these different dynamics, you maybe thought that that was a very unrealistic representation of a community being hit by an impossible number of consecutive disasters. But I think this goes to show that for many communities, this is actually their reality. And I think that's why it's really important that we try to understand all these different concepts or the different dynamics of consecutive disasters. And so I see chats coming in, I'll check it in a bit. And so Aristotle is often misquoted in saying that the whole is greater than the sum of its parts. It's other than the sum of its parts. And that's very true also for consecutive risk. For example, a week ago in Italy, a bridge collapsed. And because the corona crisis is happening, much fewer people were out there. And so you had much fewer people impacted by the fact that this bridge collapsed than had there not been a corona crisis. So it's important to realize that it's not always worsening the situation. And this is the team of people.
Thanks very much, Marleen.
Thanks a lot. You were mentioning that you received questions via the chat yourself. I'd ask everybody to send those questions to everybody so that Colin and I can kind of coordinate that. Did you have any questions, Marleen?
I'm trying to catch up on everything that's been said.
Okay. So,
Marleen, if you received a question,
No.
a couple questions by chat, we can just identify who it was, and then we can have them ask it to everybody.
Just you telling me.
Oh, okay, no questions. Got it. Okay.
Well, maybe I have a question to start things off. I think this concept of consecutive disasters is a very interesting one, and it opens up a lot of other research questions, I believe. I don't know if you've touched on that or if you looked into that specifically, but I could imagine that as the frequency of some disasters is changing locally, the flood risk is increasing in some places of the earth. Have you observed also, in addition to adapting, some tendencies of just moving away in the form of a managed retreat, essentially giving up a settlement because the frequency is just
Too much.
too high to rebuild?
This is something we're trying to look at for the Philippines. The tricky part there is that, well, data, obviously you need the migration data, but then also if you want to go very far back in time, there's less data on disasters. And so you already get, it may appear as if fewer disasters have occurred. So you'll need to compensate for that. But yeah, it's a very valid point. It's something we're trying to look at, like how, like either the frequency or like if certain people get, or if people get used to a certain hazard occurring a lot. So maybe in the Philippines, they get used to all these tropical cyclones, but then if like a volcanic eruption happens every 20 years, maybe that actually triggers migration more than it does with these like 20 tropical cyclones happening. So yeah, these are different aspects we're also looking at.
Thanks. We have another question from Kate Saunders.
Hi, thank you for the talk. I was just wondering where your data came from in your global map of your consecutive disasters.
Yeah, I don't think I put it on the slide. Apologies for that. So the earthquakes are all derived from the USGS shake map, and the tropical cyclones are the IB tracks.
Okay.
So those are the two hazards that go back like quite far in time, much further than, for example, floods in terms of trustworthy records.
I'm curious, how long do you have to wait in between before you decide that something's a different, like for an earthquake, for example, or is that just handled as part of the data set?
That's a fair question. So like I said, for the global part, we looked at 3 and 30 days. But it's such a, especially if you look locally, it's all the way at the start. I talked about Nepal, where like there was like a year and a half between an earthquake and the flood event, and still they were experiencing repercussions from the fact that they were still trying to recover. So it's so place-based, I would say, in terms of timing.
Yeah, that makes sense. Yeah, thank you.
Yeah, thanks for the question.
Hi, we have another question from
Eric.
Well, there's one raised hand before.
Okay.
From SM089627. I'm trying to unmute, which doesn't work. Maybe the person has to unmute themselves.
Whoops. All right, we can have Eric ask a question, then I was trying to figure that out as well.
Yeah, okay, let's go. Eric, go ahead.
Yeah, thank you again, Marleen, for the talk. But in thinking about the real life application of this really relevant and informative work, how should governments make this decision of preparedness? Should they be prepared for 2 disasters in a row, 3 disasters in a row? And I mean, it's terrifying to look at a place like the municipality that you pulled up in the Philippines and think, wow, it's actually possible to have all of these disasters in a row. But for a planning purpose, how would you convince governments to go to the right level of disaster risk reduction funding?
Yeah, fair question, good question. I think it really depends on a combination of how likely it is that particular hazard types occur, like how often they occur, and the extent of their expected damages. So for Afghanistan, floods and earthquakes are like the top 2 hazards, but also for the Philippines, besides tropical cyclones, earthquakes are a really important hazard. They're located along the Ring of Fire. So there I would say that it would actually have been really smart to not only focus on the tropical cyclones, but also include earthquake risk, whereas maybe the risk of volcanic eruptions can maybe ignore-ish because they happen so less frequently.
Makes sense. Thank you.
Thanks. So now SM089627.
Hi.
Maybe you can quickly tell your name and go ahead.
Sure. Yeah, Brian Golding here from the UK. The issue of consecutive extremes is, of course, important, and thank you for your talk. I just wanted to comment that there's an event doesn't have to be extreme in itself for the impact to be extreme if it's part of a series, and I think there's some issues there, both with consecutive events of the same kind accumulating, but also consecutive events of different hazards. So we have a very interesting one in the UK at the moment with the presence of COVID-19 and with the rules of isolation. A fine weekend can be a very high hazard, and if that draws people out into the countryside or to the coast, and so what would normally be benign conditions can actually become hazardous. And I think there's some interesting generalization there that might be possible.
Yeah, no, I fully agree. There's some interesting dynamics at play. For example, what you saw in Australia over the our winter season is that if rain happens after a forest fire, it's much more likely to cause a flash flood. Whereas if that forest fire had never happened, then that rainfall would not have been a flash flood. And there's many of those cases. I think Hamed Muftakhadi has an interesting paper on nuisance flooding. So yeah, I agree. It's an important but complex issue to look at.
Indeed.
I think there's a question on the chat from Victor.
Yeah, Victor's next. Great.
Hi, Dr. De Ruiter. Thank you very much for your great presentation. So I have a question regarding how you define those threshold, or determine the defining threshold for those considered events. So by intensity or by impact, for example, if you consider earthquake, what would be your threshold to define the earthquake that you consider? By PGA, or at what level PGA? Or do you consider it as an event by its casualty numbers, say 1 fatality, or economic loss?
Yeah, very fair question.
Yes.
So we looked at, we based what we included on the hazard and not on the impact, because that would feel like it's less objective. So for those global maps, we used earthquakes of an MMI of at least 5, and the tropical cyclones from the IB tracks needed to be at least a tropical storm. And so now in the maps of the Philippines, we used earthquakes of at least an MMI 8. Again, the same rule for the tropical cyclones, and the floods in the DFO, they only include floods that are damaging. So I guess there you could say that we actually used a hazard based on its impact.
Yeah, thank you. Then
that's more a matter of like lack of data than ideally like really focus on the intensity.
Yes, then my further thought is that how about the sensitivity of your results regarding the percentage of those consecutive disasters? So if you change those threshold for determining those hazards, would it be modifying your percentage in terms of how many consecutive disasters you would consider?
Probably. Very good question. We didn't calculate that, but we sure can.
Thank you.
And should probably.
I see one more question from Corey. We will have time for that. That will be the last question. And then I will have a few announcements about the upcoming seminar. and then we'll conclude. Corey, go ahead.
So my question is, very nice presentation. So a lot of what's going on in this presentation, I think, is we're thinking about combinations that have intuitive compounding impacts from from history and from what we've experienced in the past climate. But the climates we expect to exist later this century might have new combinations or new sequences that are unlike things that we've experienced in the past. So the question is, how do we start to think about the kinds of compounding impacts that'll exist for the types of sequences for which we have no intuition based on the past?
Yeah, really good question. I'm not sure if I have like a one-sentence answer to it. I think it's a really good question. I think it's really important that we think about that, although it's very challenging, I guess, to think about outside of the box type of thing. But yeah, we should think about all these different types of interactions. And I guess in some ways in recent years, we've seen more and more new types of hazard interactions that we didn't see in previous decades. But yeah, you raise a very valid point.
Okay, fantastic. Thanks a lot to all the speakers. I think this was a very nice kickoff for this webinar series. I will take this opportunity to announce the upcoming webinar, which will take place on May the 20th. We will have two excellent speakers again. First, Lisa Thalheimer, who will talk about cascading risks from climate change and forced migration during COVID-19. And then Gabriele Messori from Uppsala University talking about dynamical coupling indicators for the study of compound extreme events. So thanks again to all the speakers and participants. I think this was an excellent turnout. I saw more than 130 participants at one point, which is fantastic, really. So yeah, feel free to spread the information. You will receive the Zoom link and an additional announcement a few days before this event will actually happen. So thanks again to everybody and have a great day.
Thank you.
Thanks, everybody. Hope to see you next month.
Bye.